Everyone knows that for a polynomial in complex coefficient P, so the degree of P is n, then we know exactly have n zeros if counting multiplicity. So algebraic theorists, fundamental theorem say that if we consider for any k is algebraic closed field, so the number of zero such that it's so exactly the same with degree. So what happened for people in analytic topic? They also want to find some function present like the degree function. So that is the topic of Nevalina theory. And Hoai said that Nevalina theory is one of the few great mathematical even in the century. So actually it's a very beautiful because it has many applications and it starts from very few elementary functions. So we will tell you what is going on. Actually, Nevalina is one Finland mathematician in 1920s, and he first started for meromorphic functions. That means for a function in the low dimension. But I want to tell you about more general topics. So I will start in high dimension first, and then I will go back to what Nevalina have done. So if we consider f is a non-constant analytic curve and f title is a reduced representative of f, then Nevalina characteristic function defined by average of the log function. And this function will play similar the degree function. And another thing we call is a proximity function. It also take average of the log of absolute, the absolute value, but here we need to divide by q, and q is a polynomial, homogeneous polynomial of degree d. And another function in Nevalina theory, say counting function. And what is a counting function? Counting function is a count how many 0 points in the disk of radius t. So from this function, the first main theorem say that the characteristic function equal to proximity function plus with counting functions, plus with a constant, not depend on R. So this is very beautiful. So that means the characteristic function doesn't matter how many times or what is you take Q equal to A or any points. So another function also consider here, they take infimum of 1 minus the counting function divided by characteristic function. So because of the first main theorem, we always see this is always less than equal to 1 and bigger than or equal to 0. But the problem here, if we take many points, that means Q here, Q equal to 0. But if we take sum of Q equal to AI, so what happened? That is the question in Nevalina theory. It calls second main theorem. So the first main theorem is almost done in any case, but for second main theorems, they still have many things open. And the question here, they want to know what is the upper bow bound of this sum. Of course, we can say, okay, this is Q because every delta is a small to every one small to or equal to 1. So take sum of Q's, and of course it's smaller than Q, but we want something better, right? So another question is, if we know if we can determine a map or a function, if we know inverse of a method. So that is a two main question in Nevalina theory. So you can see it's funny to start from 2, but actually Nevalina theory, Nevalina work for n equal to 1 first. But here I want to tell you story about 1 bigger than 2 first, and then I will go back to n equal to 1 later. So Các Thăng says that if we take, because here we consider in high dimension, so we cannot consider point. So we replace to hyperplanes, and the condition in this hyperplane have to satisfy the linear independence. And then we see how big a Q is always bounded by n plus 1. So it's controlled by dimension of projective space. Okay, and the people want to generalize this problem either Pn. Now we can consider for any algebraic variable variety of any dimension, and also a hyperplane will consider by hypersurface. So what will happen? Okay, and then the first result in that direction is a finding by Shipman, and he considered for di hypersurface in general position, and P here is he needs finite order, and also is not degenerate in any hypersurface. And I will tell you what is a general position mean. So go back to the hypersurfaces. So in P2, so hyperplane in P2 is only line. So we have 2 lines. So if we close eye and we draw one other line, okay, that's close eye. And very luckily, intersection of 3 lines have to be empty. And if we want intersection cannot be empty, we have to be very carefully draw it, go to this way, right? So mean general position, we can draw very freedom, but not general position, we have very carefully to draw it. So in math mean when you cut one time, the dimension will reduce 1, okay, until it become empty, okay. So that is the meaning of general position. So when they apply this condition to the result, the Eremenko obtain that if F is a map into projective space and the image is not degenerate in the DI, and of course from now I will assume DI as general position, then he also contain obtain that the bounded have to be 2n. And this is still not strict enough. And then Zhu in 2002, he worked for X here is a projective space, and in 2009 he worked for any variety, and he got better bounded here. So here is n plus 1 replaced by 2n here, okay? But the problem here, he needs F to be algebraically non-degenerate. And in this result, they only need to non-degenerate in hypersurfaces. So the condition is a little bit stronger here. And we also don't know if only use this condition, the bounded can be this one or not. So it's still an open question for everyone here. Okay. And then there's one famous conjecture given by Griffiths that the bounded should be n plus 1 divided by the dimension of variety. Of course, this is a very hard problem and still no any progress on this question there. So now we go back to Nevalina result. In 1926, he first worked for n equal to 1. And what he got here is a 2. Okay. Then the problem here, oh, sorry. So AI, here, Nevalina worked for the constant. So the question now, we want to work on moving targets. That means AI here is not constant anymore, but general is a small function. So the question is, what is going on? So there are several results about that, but no one until 2009, and Yamanoi, one Japanese mathematician, is find out very nice result. This actually quite hard paper. It published in Acta Math and over 60 pages. And our try, even we opened one seminar to read his publication, and actually very difficult to understand what step by step. Anyways, it's a very nice result, and he can give the bounded. Oh, sorry. What we? Yeah, the bounded. If we consider for small function here, so the bounded also 2. Okay. So what I want to do is I want to translate the question from complex K into non-Archimedean field, because we know for non-Archimedean field, the absolute value is much stronger. So it's not the sum, absolute value of sum is not the sum of absolute value. It's have to be smaller than the maximum, okay? The maximum of each absolute value. So also have one theory about Nevalina theory for non-Archimedean field. So my advisor, Hoai, is the first one translate from complex into non-Archimedean field, and his paper is published in Duke. Then everything step by step follows a complex. So we also define for characteristic function, proximity function, and also counter function. So for counting function, exactly the same with complex K, but for characteristic function and proximity function, here we don't need to take average, because in the non-Archimedean absolute value, so if one get into the disk, so it have to get into only the bounded. So we don't need to take absolute average here. And then they also want to get similar result from complex into the field of non-Archimedean, and then very similar, we get this one. Okay, and in 2004, Ru also consider for GI hypersurfaces in general position, and the bounded here replace from n plus 1 in complex K by n in non-Archimedean K. So remember here, he only consider for projective space. So the question is, if we consider for any variety, so what is bounded here? So this is my result. I replace the projective by any projective variety of dimension n. I also get strictly bounded here already. And then as corollary, so from that result, we also can say very strong that there are only at most n hypersurface such that is bigger than 0. So even much stronger, okay? Not only some stricter length than n, even at most n positive here, or almost are 0. And then also related to hypersurfaces problem, we also can prove that if we omit big enough hypersurface in general position, so this space have to be hyperbolic in terms of Brody. So yesterday we also listened about hyperbolic, but it is in terms of Kobayashi. So hyperbolic in terms of Kobayashi will imply Brody hyperbolic, but another way is not. So here we only get this one is a hyperbolic, Brody hyperbolic, okay? And Brody hyperbolic means no any non-constant map get into that the space. So now we also want to work similar with Amanoy problem. That means for the K of Ri is a small function, and then unlikely we cannot get exactly. So in Amanoy result here is a 2. So normally for non-Archimedean the number should less than 1. Okay, but we still cannot get 1 here because there are some technical in complex K cannot translate into the non-Archimedean case. And then we also cannot find another way to pass into difficulties gap. However, we get something not so perfect, but also good enough. Here we get something like a 2 cube over 5, and from this one, and we get corollary say that if 2 non-constant meromorphism functions share 5 distant small functions, then they have to be the same. And this result improve the result of Alan S. Kashid and other author where they only consider bigger than or equal to 7. So here we can get into 5, but what we want to do is should be 4 here, but we still cannot get it. And this result, I work with my student. He's just graduate PhD some week ago. And then another thing related to this topic is Brody hyperbolic. That's I mentioned about on corollary. And now I want to say a little bit more general case. And one manifold called hyperbolic if there are non-constant map from F into X. So F here either complex field or non-Archimedean field. Okay. So Kobayashi and Zeidenberg conjecture say that for generic hypersurface of degree at least 2n plus 1 should be hyperbolic. But this is still open conjecture, and people get very few in this direction, very few result in this direction. And I will mention a little bit. So Green says that the complement of 2n plus 1 hyperplane in general position is a Brody hyperbolic in complex K. And then Eremenko-Sodin also prove that complement of 2n plus 1 hypersurfaces. So here is a hyperplane and here is replaced by hypersurfaces, and two papers appear in the same time and independent. They only use a different method but get the same result. Then after that, people, because we cannot get for general case, so people try to get for for lower dimension first. Okay, so for example, in P2 omits the 4 curve and then is a hyperbolic, or P2 omits 3 4 line and here is a 3 curve and is a hyperbolic. And this paper appear in American Journal of Math, and also the second one in the Duke of Math. Okay. So the same like before, we also want to do for non-Archimedean case. So rule theorem say that Pn omit n plus 1 hypersurfaces is a hyperbolic. And also my corollary says that if we consider for any variety here, then we omit n plus 1 hypersurfaces. So it is a hyperbolic in non-Archimedean field. So similar Griffith-Zeidenberg conjecture, we also give a question here. So is the Pn, or maybe more general, is X omit Q generic hypersurfaces is a hyperbolic. And we got some result about this, and very sorry, the last professor in Notre-Dame, he already passed away very few years after this paper appeared. And here we also can get, if it is any projective non-singular variety, then if we omit big enough hypersurfaces, so here we need to omit at least n plus 1 hypersurfaces in general position, then we get the answer. Okay, and the number here is the best because if we reduce to n, then we can give a count example. So if Pn omit n hypersurfaces in general position, then it is not hyperbolic, because we can find one map from K into here, and of course this is not constant. Okay, so but because here we take all a line, so that means the dimension 1. So the question, if we cannot reduce the number of hypersurface, so we increasing the degree, right? Because if we reduce the number, so we can choose the degree is low and is not. But what happens if we choose the degree is bigger? So likely we have some result if increasing degree. Okay. So to do that, at first we need the definition about intersection transversally. So what is a intersection transversally? By definition is that, but you can see in the picture. So there are two curves. So if they intersect like this, it's not transversally, because they are one common tangent here. But if it's do like this, so it's transversally. Okay, so this is not, and this yes. So which if we restriction on hypersurfaces satisfy this condition, then we can get something better. For example, if so Pn of this n here, and the dimension only need to bigger than or equal to 2. So you don't take line anymore. You take for example, quadratic curve, and it's enough. Okay. And also, we give an example to prove if we only take only one is a line, so it's a counter example. So this is the result is the best here. Okay. So, but what we want to do is a Griffith-Zeidenberg conjecture for non-Archimedean case. That means we need to satisfy and necessary condition. So right now we only get sufficient condition, right? We don't need, we don't know if it's necessary and sufficient condition or not. And then we only can work for the k of n is a 2. And in the k n is a 2, and then we can get something. And here is the result. And it says that in P2 of this 2 hypersurfaces intersect transversally, and the degree bigger than or equal to 2, or one is a line and another have to degree bigger than or equal to 3 is enough. And then also if intersect not in any maximum flexion point. And this is also general condition. That means very few hypersurface satisfy this one. So that means this condition, this theorem satisfy for very large hypersurfaces. Okay, and then interesting here, the converse way is the only omits these 3 cases. And the first case is so that means this is not hypersurface, hyperbolic. So the first case is one is a line and another is either line or quadratic curve. So if 2 lines, we have 2 lines, D1 or D2. So we always can find one map such that in F is a line on this way, and only of this one point is the intersection point. So it's not. So P2 of this to D1, D2 is not hyperbolic. And this is the first case. And also in the first case, if D2 is a degree 2, then we have this. And there are 2 ways. The line, so here is a D2. So D1 here, either intersect D2 into 2 points. So we also can take a map such that in F lie on the tangent go to the intersection point here. Okay, and another way is the same. If we have here is a D2 and here is a D1, so we also can take many here. Also omit 1 point here. Okay, so that means either, sorry, this way is not appear here because we have to satisfy intersect. So okay. Then another way is one. So there are 2 dimension 2. So we have 2 is a dimension 2 and intersect transversely. So we can take F is here. So in F So it's the K2 is here. And the third is one is a lie, another is a bigger degree bigger than or equal to 3. So what we have is this. So we have a curve and another is a line. And here we can take the tangent here. So IMF is this one. Of course, these are only pictures you can imagine, and we prove by formula. So from this one, we get the Griffith-Zeidenberg conjecture for only the K of P2. Okay, so if D1 and D2 are generic curve in P2, then complement in P2 is a hyperbolic. So all of these results also can translate to integral solution of curve, which number theorists are interested in. And we also have publication about that here. And I work with Levin and my postdoctoral advisor. And as you can find, if number theory interested in, you can find on this paper. Okay, so there is the reference related to my talk. And thank you very much for attention.
Thank you very much for interesting talk. And are there any questions or comments from the audience in person?
Yes.
Yes, please.
I had a very basic question, not the sophisticated thing. I had a very basic question.
Yeah.
So I know this correspondence between divisors and line bundles.
Yes.
So this defect you talked about, delta F,
Yes.
what does it mean when you think of the hypersurface as a divisor of a line bundle?
Yes. Actually, also people work for any line bundle for ample divisor.
Sorry?
So hypersurfaces is similar to ample divisor.
Yeah.
So there are also result on that. So people also work on ample divisor.
Ample divisors.
Yeah.
So you're saying that delta F can be defined and all
Yeah.
these theorems
Yeah.
can.
Yeah. Very, of course, much more complicated.
Much more complicated.
Yeah.
I see.
That's why it's much more complicated, but can translate automatically.
Oh,
okay. So that's why people prefer to work on hypersurface related to ample divisor.
Yeah, because it translates directly.
Yeah.
Okay.
And technique is a very complicated, and result is not so much different. So people want to show up on what is easy to imagine, right? So here you can see on picture.
Yeah.
Yeah.
And another quick question.
Yeah.
Like instead of F, if you take a section of another line bundle,
Sure.
can you do that also?
Yeah.
That has also been done.
Yeah.
Okay.
So geometry, complex analysis people also work on that.
Okay.
Yeah.
Okay, great. Thank you.
Thank you.
Any other questions? I have one.
Yeah.
What happens for Archimedean case?
So Archimedean K means complex K.
Uh-huh.
Yeah.
Oh,
Yeah.
I see.
So complex K is Archimedean. And
I see.
non-Archimedean means like periodic field. Yeah, it's a non-Archimedean. Yeah.
I see. Oh, thank you very much.
Okay.
Yeah. And are there any questions online audience? Maybe not. Then let's thank the speaker again.
Okay, thank you very
Thank you very
much.
much.